Hello. You know that there are different types of strings and they seem to be very distinct. In this video, I try to give a short summary on how to look at them. Here we have two cases where I'm going to divide left and right. And here I talk about infinite string or semi-infinite string, and the right I talk about clumped strings like fixed ends or finite string. And I would like to point out some similarities and difference between these two and how to look at them as something which comes from the solution of the wave equation. So here we have a situation which can be in case of infinity, or can be either infinity here or semi-infinity, where you have a fixed position, so this end is fixed, or you can also have fixed in the sense that it's there is an end, the string has an end, however it's free to move, and so it can move up and down here by many ways. One, for example, is by attaching a string ring to somewhere and then allowing this string to go up and down. But here, this one is the clumped one, where you have, in the cases of a drum, for example, where you have both ends attached. And first thing is the buff, as I just mentioned, the buff can be treated from the solution of the wave equation in one dimension, which you know a little bit more after watching the previous video on wave equation in one dimension. And the point here is that D'Alembert found the solution, found that the wave equation on strings can be derived from two pieces of information or two pieces of work, namely Newton's work or Newton's mechanical laws from dating from 1686 and from Taylor expansion from 1715. So then D'Alembert came with a solution which is dated from back to 1747 or so ish. And this solution is, because I'm keeping it to the left, it's related to these situations, or it's more natural to apply to these situations. And the first one here is the D'Alembert solution. And we are talking here about solutions being strong. As we mentioned before, we have strong classical solutions or weak solutions, but here we're just talking about strong solutions. Another solutions, the ones related to this situation here, clumped string, comes from Bernoulli solution. And the difference here, you see here there are a couple of years, and one, it's based on something called the change of variables, or it's also related to the method of characteristics in partial differential equations, and the other one is related to the separation of variables method. In the case of the D'Alembert, usually it's more natural to apply for Cauchy initial value problems, where we don't have boundary conditions. And in the case of Bernoulli's is an initial boundary value problem, as we mentioned before, where we have initial data and boundary conditions. And these boundary conditions are specified at the fixed positions, namely XA and XB, according to this picture. For the Cauchy initial value problem, we have initial position where we denote by f of x, as we mentioned before, and phi of x 0, and then we set time is equal to 0, so this is the initial position. And then we have our initial velocity, where we set time is equal to 0 on the derivative of phi, and then after taking the derivative, set is equal to 0, and this is our j of x, namely our initial velocity function. A particular thing here is that we are talking about one-dimensional wave equation. However, the D'Alembert solution can be even used as a very general solution. It can be even used for three-dimensional case, for example, where we can reduce by change of variables three-dimensional problem to one-dimensional problem along a radius, radial distance, radial direction. And here I have both of them more or less. how can I write them? Here I have the D'Alembert solution. So my phi as a function of x and t, it has it depends on initial positions, as I define initial positions, and depend on initial velocities. And in previous video, I mentioned that for the hyperbolic differential partial equation, we have two real characteristic directions, and these characteristic directions are actually implied here. We have x plus ct and x minus ct, and they have to do with the what we call the forward or right moving wave and the backwards or left moving waves. And here we have sort of say mean value. So we have this initial position evaluated at one of the fronts, so evaluated at x plus ct and evaluated x minus ct, and then we take the average. And here we also have a kind of average, but here is on the light cone. So when you study special relativity, we know that x minus ct and x plus ct forms a cone in Minkowski space, and basically we are integrating from inside this cone, and here's the initial velocity, and this has to do with some kind of average value. However, because it's not like Laplace equation where we can apply the mean value theorem, and there we have an elliptical differential equation. Here it's not elliptical, here it's hyperbolic. That is not exactly just this mean value as we would have in the case of D'Alembert or Laplace, sorry, in the case of Laplace. However, we have this nice combination between initial positions and initial velocity, and we see that the position, they are evaluated at 2 points, but the velocity is average along all the way between these 2 points, because this is an integral. Yeah, so here this solution, it's worth an entire video just to talk about the D'Alembert solution, I would say. Now, for the right side, we have Bernoulli solution, as we just mentioned, and here basically we have an ansatz where we say that our solution is a function of space and time, and we say that we can split it x and t, and we split it. This function only depends on x, and this one only depends on t. And then we try to see if that's a solution and how it proceeds like this. Basically, you feed back these ansatz inside our wave equation, and we apply boundary conditions thereafter. And these boundary conditions, they are what? They are some constraints about space, constraints about these 2 points here, which are fixed. And we consider superpositions. Linear, we are talking about linear differential partial equations of second order. So after applying the boundary conditions and having sort of solutions, we have to take a general solution which has to do with superpositions. And then upon when we have already the superposition, at the end we use our initial conditions upon it. And this has to do, it's something about time, but we need to use our initial conditions and our boundary conditions here in order to be able to solve that. So I would like to stress again the role of superposition here. The next point is about why one is about traveling waves. You can clearly in natural see that the D'Alembert solution is describing traveling waves, as I mentioned, forward and backward, or right moving and left moving. But here they are of any shape. We don't specify a shape at all. Here, in the case where you have the fixed points, we are talking about standing waves, in the sense that they cannot, the wave cannot propagate because it's fixed, but it's composed of a superposition of many modes or harmonics. So you have first harmonic, second harmonic, and third harmonic, where basically first harmonic it's I will see in a minute, but a point here is that one talks about N shape and the other one talks about waves, harmonic waves, which could be sines and cosines, but they are harmonic functions. And the relation, how can these two things be described or be related to the same thing, namely the wave equation, has to do with Fourier analysis. So Fourier analysis makes the connection between this n shape and harmonic functions. And of course, Fourier series is included in this Fourier analysis. But now there are some similarities as well. So for example, if we're talking the speed of the wave and the strings, the speed depends on the material properties, so it depends on the string itself. In both cases, the same, either as infinity or finite or semi-infinity, which is this case here. But the velocity is, as we said before, is just the square root of t over whole in the case of the string. I left it open here because for solids we have the Young modulus, but for sound waves we have the bulk modulus, but for a string is just our plain simple T of tension. Now, why in the case of the infinity string we have like could be someone or some machine perturbating, so creating a wave. So in that case, the source determines the frequency. So the frequency is determined by the source. In the case of the fixed strings, what is fixed is the wavelength. So the wavelength is determined by the boundaries. Once the boundaries are fixed, like in this situation of this one or this one, and then there is a wave there, the shape of the wave is already determined because in the case the wavelength is determined. For example, here the first harmonic, the lambda or the wavelength is 2L. In this case, for example, it's just L. So in the case of the clumped string, what is already determined is the wavelength. So here is the frequency, here is the wavelength. However, because of this relation, namely how we relate frequency and wavelength to the speed, and speed only depends on the properties of the material of the string, here from the frequency we can find the wavelength. Here from the wavelength we can find the frequency. And they are both related because of that relation, key relation, which is the speed of the wave propagation. Now, while the infinity string is more natural to solve using the Lambda solution, we can also use a semi-infinite string. In the case of the semi-infinite string, we also have a boundary condition, as you can see from the photo, the picture. So for example here, of course, we have some boundary conditions here, namely this point is fixed. So we need to make sure that this, we come into the equation to say that this point, let's say x is equal to 0. At that point, the function phi, which determines the wave positions, it's 0. So that's a boundary condition, right? And here we also have a boundary condition, namely that the tangent to the string at 0, that should be an horizontal. And so back here, we still can use the Lambda solution to solve these situations, for example, naturally without much trouble. Basically, because if we have here the Lambda solution, and we say, let's say that we have a function initial position which is odd function, and also our initial velocity is odd, then there is a property that our solution will be odd. Now, if our initial positions are even functions and also our initial velocity is an even function, you have here as an even solution. So based on that property of the Lambda solution, if we want to solve, for example, the case of free to move end, basically the derivative with respect to x for all times, but at 0 is equal to 0. That means the tangent to the string, so how much phi change with x. So it's 0. When you are studying these situations, you usually this boundary condition, and the only function, a function which can fulfill this condition is an even function, for example. And so we can use extensions. We can consider extensions of our D'Alembert solution, in order to fix or to ask it to be even or odd in particularly. For example, in the case of a fixed n, what we want? We want phi at position 0 for all times. We want this is equal to 0, right? And this can be accomplished by an odd function, because we know, for example, for an odd function, f of x is minus f of minus x, right? So then that means that f of 0 is 0. So somehow we can achieve this with even functions, while for the free to move end, we can do that with even. So here is with odd and here is with even. And just to repeat again, you can see I'm just talking about these to be our free to move one, and here is our fixed one, and they are exactly what I just mentioned here and here. So we can work with these extensions. Now, for the case of D'Alembert, for the case of Bernoulli's, we actually need to separate a PDE of any variables into any independent ODEs. So basically, in our case, we have a second differential partial equation. So we will get two ordinary differential equations, one for time and one for the space. And that's the method of the separation of variables. Something else here important to remind is that the boundary conditions are linear and homogeneous. If your boundary conditions are not homogeneous, namely if you have a term which is constant, is not proportional to the function or to the derivative of phi, in that case we need to do some things in order to get, always can do that, and then we get an homogeneous from the non-homogeneous, and then we proceed again using this method, which is the our method of Bernoulli solution with separation of variables. But you must remember of always keep it homogeneous at first. And this separation of variables has to do with separation in time and separation in space, and this means this has a strong relation to symmetry. Usually this symmetry can be with respect to translation or with respect to rotations. Sometimes you look at the problem and you see that if we are talking about three-dimensional space, for example, you can see that along one direction something happens, and on the other two directions, for example, nothing happens. So somehow you know that you have some symmetry in one direction, but the other ones are not affected. So there is this nice relation between symmetry and separation in time and space. So this solution of separation of variables is not always possible. It's a very particular and special property and condition. And what links separation in time and space, or this method, with symmetry is group representation theory. So when you start the representation theory of the symmetry group of your wave equation or your differential equation, you'll find that these symmetries is especially related with this possibility of splitting the solution with the separation of variables. I hope it was helpful. If you want to follow the next videos, you can consider to subscribe and leave a comment or a question below. Thank you for watching and see you next time.